Hello everyone, this is a presentation on Thevenins Theorem by Charles Betancourt for the class ECET110, week 7. So what is Thevenins Theorem? Thevenins Theorem states that it is possible to simplify any linear circuit, no matter how complex, to an equivalent circuit with just a single voltage source and series resistance connected to a load. It is especially useful in analyzing power systems and other circuits where one particular circuit, called the load resistor, is subject to change. Thevenins theorem in power systems. The theorem is useful in power systems where one particular resistor, known as the load resistor, is subject to change and recalculation of the circuit is necessary with each trial value of load resistance to determine the voltage across it and current through it. Now looking at the circuit example to the right, suppose we decide to designate R2 as the load resistor for this circuit. Instead of using other theorems over and over and wasting time to find out what happens if the load resistance changes, we can apply Thevenins theorem. Now changing load resistance is very common in power systems, as multiple loads get switched on and off as needed. The total resistance of their parallel connections change depending on how many are connected. The Thevenin equivalent circuit. Thevenins theorem makes it easy to analyze different scenarios by temporarily removing the load resistance from the original circuit and reducing what's left to an equivalent circuit composed of a single voltage source and series resistance. The load resistance can be reconnected to this Thevenin equivalent circuit, and calculations can be carried out as if the whole network were nothing but a simple series circuit. Now here figure A shows the original circuit, while figure B shows the Thevenin equivalent circuit with one voltage source and one series resistance. Thevenin equivalent circuit part 2. The Thevenin equivalent circuit is the electrical equivalent of B1, R1, R3, and B2 as seen from the 2 points, from where our load resistor R2 connects. If the equivalent circuit is correctly derived, it will behave the same as the original circuit formed by B1, R1, R3, and B2. In other words, the load resistor R2 voltage and current should be exactly the same for the same value of load resistance in both circuits. Now, the load resistor R2 cannot tell the difference between the original network containing B1, R1, R3, and B2 and the Thevenin equivalent circuit of E Thevenin and R Thevenin if those values were correctly calculated. And as you can see there, E Thevenin and R Thevenin are written in the same way as like R1, R2, and it's a good way to know that that has been simplified. Calculating equivalent Thevenin source voltage and series resistance. The obvious advantage of performing the Thevenin conversion to a simpler circuit is that it makes load voltage and load current so much easier to solve than the original network. Calculating the equivalent source voltage or resistance is actually quite easy. First, as seen in the image to the right, the chosen load resistor is removed from the original circuit, replaced with a break, which is an open circuit. And you can see it in the picture where we removed resistor R2, which is the load, and it is now an open circuit. Determining Thevenin voltage. After removing the chosen load resistance, the voltage between where the load resistor used to be attached is determined. In this case, the original circuit with the load resistor removed is a simple series circuit with opposing batteries, so applying Ohm's law and Kirchhoff's law can be used to find the voltage across the open load terminals. And as you see to the right, they took care of that for us. Determining Thevenin voltage part 2. Now, after removing the chosen load resistance, the voltage between where the load resistor used to be attached is determined. In this case, the original circuit with the load resistor removed is a simple series circuit with opposing batteries, so applying Ohm's law and Kirchhoff's law can be used to find the voltage across the open load terminals. The voltage between the two load connection points can be figured from one of the battery's voltage and one of the resistor's voltage drops, which comes out to 11.2 volts in this case. And this is our Thevenin voltage, also known as E Thevenin or in our case V Thevenin. Determining Thevenin series resistance. To find the Thevenin series resistance for our equivalent circuit, we need to take the original circuit with the load resistors still removed, remove the power sources, and figure the resistance from one load terminal to the other. With the removal of the two batteries, the total resistance measured in this location is equal to R1 and R3 in parallel, and this is the Thevenin resistance, also known as R Thevenin. And finally, determining the voltage across the load resistor. With the load resistor being 2 ohms attached between the connection points, we can determine the voltage across it and current through it, as though the whole network were nothing more than a simple series circuit. If you notice, the voltage and current figures for R2 are identical to those found using other methods. Also, the Thevenin voltage and current figures do not apply to any component in the original complex circuit. Thevenins theorem is only useful for determining what happens to a single resistor in any network, the load. And to the right you can see that the Thevenins, the values don't match any of the single components in the original circuit. However, it is still a useful determination of the overall circuit using different scenarios without having to do the same math over and over. So this is actually a really cool law to use. This is my references page where I got the information and pictures used in this presentation. I hope it was helpful and that you enjoyed listening to it. Thank you.